Hello, and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be doing Unit 6, Lesson Number 9 on trigonometric limits. It's been a little while since we've done limit work, so we're going to have to remember some very basic ideas about limits and about continuity, and then we're going to get into one very special trig limit. As always, you can click on the description underneath the video in order to obtain a worksheet that goes along with this video. For now, though, let's take a look at the fundamental setup. So, trig functions act like a lot of other functions in that their limits are, generally speaking, very easy. So for instance, in exercise number 1, letter A, we're asked what is the cosine of 2 theta as theta goes to 0? Well, generally speaking, right, if you can picture the cosine 2 theta function, it's nice and continuous. So we can actually just find this limit by simply doing substitution. The cosine of 2 times 0, which is the cosine of 0, which ends up being 1. Why don't you pause the video now and see if you can do letter B. Alright, well hopefully when you looked at the limit of 1 divided by 1 plus sine x as x goes to pi over 2, right, the first thing you should try is substitution. Since the sine of pi over 2 is equal to 1, this limit is no issue. It's 1/2. Alright? So generally speaking, like always, when you're thinking about a limit, when you're thinking about what value the function is headed towards as the input heads towards a particular value, well, ask yourself, is the function continuous there? Can I just evaluate it by substitution? Now, of course, where continuity often becomes a problem is when we deal with piecewise functions. So let's take a look at exercise number 2. Exercise number 2 tells us that we've got the cosine function when x is less than 0, and we have the sine function as the output when x is greater than or equal to 0. And the first question asks us to find the limit of f of x as x goes to 0 from the positive direction, right? That little 0 with a plus on it. Now remember what that means is that what we've really got going on is 0 on a number line, the x-axis specifically, and we're going to approach 0 from the right. So what we have to think about in our piecewise defined function is which part of this function am I on? And where I'm on is sine x. So I can say that this is simply the limit of sine x as x goes to 0. Really, just as x goes to 0, but I'll put 0 from the right. And then that's going to be the sine of 0, and that's going to be 0. So the limit of f of x as x goes to 0 from the right is 0. On the other hand, here we're asking what are we going to get as we approach 0 from the left? Going back to our little number line, right? Here we're going to be on the cosine function. Again, some students might get confused about this because the equality is not included on the 0. But remember, we can get as close to 0 as we want from the left, just not all the way there. So there's absolutely no issue with saying that this will head towards the cosine of 0, which of course has a value of 1. All right? Look at letter C. See if you can figure out what the answer to this one is. Pause the video now. Alright, well anyone that's been exposed to limits before has seen this question about 100 times. Does this limit exist? The limit as x just goes to 0. Now remember what that always implies. The very definition is that coming from the left and coming from the right, you're headed to the same number. But notice, coming from the right, we're headed towards 0. Coming from the left, we're headed towards -1, and therefore the answer is definitely no. The best explanation for that, in my mind, the why or why not, is simply symbolic. The limit of f of x as x goes to 0 from the left is not equal to the limit of f of x as x goes to 0 from the right. Now, it also asks us, what does it tell you about the graph of f at x equals 0? Think about this. Well, there's a nice word to describe this. Pause the video if you need to. What the fact is that the limit doesn't exist. That fact then implies that f will have a discontinuity. Or be discontinuous at x equals 0. In fact, you can actually sketch a little bit of this graph, right? It's cosine x when x is less than 0. So it kind of looks like this. Right, and it goes on forever. And yet it's sine x for when x is greater than 0. Right, so it looks something like that. So right here at x equals 0, we have that discontinuity. All right, so again, all of this basic limit work really doesn't involve anything that's all that special. I'm going to scrub out the text in just a moment, so pause the video now if you need to and copy down anything that you may have missed. Okay, scrubbing out the text. Let's go on. Let's go on to the next page. Okay, so let's see how much you understood of that discussion. Now we've got one of these classic questions. We've got a piecewise defined function with a missing parameter. In this case, it's called k. So the function is 5 times the cosine of 2x plus k when x is less than 0, and 9 minus x squared when x is greater than or equal to 0. And we'd like to figure out the value of k that will make the function continuous right at x equals 0. Why don't you pause the video and take a shot at this? All right, I'm going to go through this in a very technical way. All right, the technical definition of continuity, or a function being continuous, is that the limit of f of x as x goes to 0 must actually be f of 0. So that's the technical definition. Now, the weird thing, though, is that as x heads towards 0 from the right, we get the same thing as, oops, I should be using g. We should get the same thing as g of 0 because the equality is included in the right-hand limit. So really what we just have to make sure of is the limit of f of x as x goes to 0 from the left, and I keep using f where it's actually g. Sorry about that. The limit of g of x as x goes to 0 from the left, that's got to be g of 0. All right? Well, the limit of g of x as x approaches 0 from the left, well, that's going to be 5 times the cosine of 2 times 0 plus k. And of course, g of 0 is 9 minus 0 squared. Here, 2 times 0 is 0. The cosine of 0 is 1. So we get 5 plus k is equal to 9, and k must be 4. All right? It's kind of cool. Again, you know, like in terms of graphing, I think that most of us have a pretty easy time picturing this parabola, right? It's up here at 9 units, and it just does something like that. The trig curve, though, that's a little bit trickier, right? And what we end up finding is that as long as that k is 9, then that trig curve, that cosine curve, will meet up with it. We could talk about amplitude and frequency and period and all of that, but we're not going to go there. All right? So I'm going to scrub out the text, and then we are going to get ready to look at the most important trigonometric limit that there is. So pause the video now if you need to. Okay, the text is going to get scrubbed. Here we go. All right, let's take a look. Unquestionably, the most important trig limit, fireworks, is the limit of sine theta divided by theta as theta goes to 0. Now, this is quite possibly the most famous limit in terms of limits anywhere. So what I'd like to do is come up with a conjecture. What is this limit equal to? And then we're going to prove it. And we're going to come up with that conjecture by doing exercise number 4. All right? Now, letter A, that should be simple enough. Why can't you find the limit of sine theta divided by theta as theta goes to 0 by substitution? Pause the video for a minute and think about that question if it's not obvious. Well, if we attempt to do it by substitution, hey, why not, right? We'll get sine 0 divided by 0. The sine of 0 is 0. And 0 divided by 0, right? Weird. And yet, almost every limit that has been truly interesting that we've come across in this course upon substitution has been 0 divided by 0. So now, let's use our calculators and experiment. Hopefully, you've used a calculator before to investigate a limit. What I'm going to do is I'm going to ask you to pause the video now, take your calculator out. In y1, put in, I suppose it'll be in terms of x, sine x divided by x. Watch the parentheses use here. And then set up a table to explore what this limit is if the angle is measured in degrees. And then just put your calculator into radian mode and experiment with what the limit is when your calculator's in degrees. All right? Pause the video now, and then we'll take a look at it on our own calculator, okay? Well, if you did this right, it'll take a little while. And if you did it right, what you should have found was a very messy answer for this, and about the nicest answer you can possibly have for that. All right, so let's take a look. Now, this is a good review of just how to do limits in terms of calculators. So I have to bring the calculator out now. That always takes me a little bit of time. Okay, all right. So we have our calculator. Obviously, what I'm going to do is I'm going to go into y equals. I'm going to clear out anything that might be there, and I'm going to put in sine of x divided by x. Remember, you have to be careful about those parentheses. Okay. Now what I want to do is I want to examine a table. So I'm going to go into my table setup, right? And I'm going to start my table at a target value of 0. Now I want to get very, very close to 0 from both sides. Okay? So what I'm going to do, oh, I forgot. I got to make sure that I'm in degrees. Hold on for a second. Mode. Put myself in degrees if I'm not already there. And now let's go back into the table setup. Okay, so the table starts at 0. All right, and I want to get very close to it, so I'm going to make my delta table very, very small. 0.01, 0.001, whatever. So let's change that. Now let's look at some values. Go into my table. Maybe scroll up a little bit so that I can look at coming from both the right and from the left. Okay. And what I see in this table, right, is it's a little bit of a mess, you know? But it does seem pretty consistent, and in fact, it's a number that's about 0.01745. You'd think I'd have that memorized after all these years. Now the cool thing is, look what happens in radians. Now this is going to be easy to do because all we have to do is go back into our mode, go down, put our calculator in radians. I'm going to go back into my table really quick because oftentimes, my table setup that is, oftentimes I have to make sure to reset this. So table start at 0, delta table 0.01. All right, let's go back into our table. Oh, that's much nicer. Look at these values. Right, look at the values from above. Look at the values from below. Whew, they all seem to be heading towards one very nice number, and that's the number 1. All right. I'm going to make the calculator go bye-bye now, and it's gone. All right. So, a lot of times in previous courses, we've always said trig modeling is done in radians. Calculus with trigonometric functions is done in radians. And believe it or not, that one value, the fact that the limit of sine theta divided by theta as theta goes to 0, nowhere else, the fact that it goes to 1 is the linchpin in all of it. Now, side note, and this is kind of cool, if you're wondering why that number, that is actually the conversion between degrees and radians. That is equal to pi divided by 180, which is kind of cool. Anyway, what we're now going to do for the rest of the lesson, this is absolutely it, all right, is we're going to prove that limit. So pause the video now if you need to copy any of that down. Okay, I'm going to scrub out the text. All right. This is one of the most important proofs in all of mathematics, and it really is very, very geometric. It's kind of super cool, to be honest with you. So I'm going to have to draw a picture. Hopefully it's going to be a decent picture. What in the world happened to my pen? There it is. I just botched the y-axis right from the beginning. All right, so what I'm going to do is I'm going to actually draw just a little chunk of the unit circle. Okay, I'm going to draw the first quadrant of the unit circle. This argument could be made in any quadrant, but it's going to be easiest to make in this quadrant. So I'm going to have a 1 there and a 1 there. Now what I'm going to do is I'm going to do that kind of classic. I am going to draw a radius, but I'm going to actually overextend it, okay? And I'm going to draw 2 right triangles. One of them is going to be right here, and one of them is going to be tangent to the circle, so it's going to come right down to there. All right. Now, there's really 3 things on this picture that I need you to sort of concentrate on, and let me put a little theta in there. All right, we have a smaller right triangle. All right, and by the way, remember, this is the unit circle, so this distance is 1, right? So we have the smaller right triangle, okay? We have a bigger right triangle, And what do we know about that? We also know this is theta. Sorry about how bad these right triangles look. We know this is 1, right? Think about it, right? That's this here. And then finally, and this is the kicker, we also have what's called a sector of a circle. Or as I like to think of it on a Friday night, a slice of pizza. Okay, that's this thing in here. I don't really want to start coloring this in, otherwise it's going to start to look crazy. Now, I hope that you can appreciate this statement. The area of that sector, okay, let me put sector down in here. The area of that sector falls in a particular inequality. It is definitely bigger than or equal to the area of the small triangle, right? And the reason I can say that is because the small triangle lies inside of it, and it must be less than or equal to the area of the large triangle. And that's because it lies inside of the large triangle, right? That's just a common sense notion of area. So what we're going to do now is we're going to figure out the area of the small triangle, the area of the sector, and the area of the large triangle in terms of theta and some trig functions. Let's start with the small triangle, this thing. Now, as we all know, right, area of any triangle is 1/2 of its base times its height. But the base of this small triangle is, by definition, the cosine function. And the height is, by definition, the sine function, right? That's just the definition of sine and cosine. So the area of the small triangle is 1/2 cosine times sine. Let's now work on the area of the larger circle. This one's a little bit harder to figure out. Now, that's kind of ironic, because in terms of 1/2 base times height, we already know one of those two. The base is 1. The question is, what's the height? I'd like you to think about that for a minute. What would the height be in terms of theta, and specifically in terms of a trig function that involves theta, right? Think about that. Pause the video if you need to. All right, hopefully what you figured out is this is actually tan theta. If you don't believe me, think about it for a minute. The tangent of theta is always the side opposite divided by the side adjacent, and therefore the tan theta is tan theta divided by 1. Got that? I know that seems strange, but think about it a bit, right? So that's going to be tan theta. All right, and the area of the sector, I'm now gonna like take this down here. All right, let's play around with this down here. Now, I think I can solve for the area of the sector as a function of theta by setting up a proportion. I might say that the area of the sector is to the area of the whole circle. Well, that would be theta to 2 pi. Now again, because I am working in radians, right, I'm just looking at the ratio of that central angle to the total, right? But that means the area of the sector is equal to theta divided by 2 pi times the area of the whole. But what is the whole area? Pause the video for a minute and think about what is the area of the entire unit circle. Did you figure it out? The area of the whole unit circle is equal to pi, right? Pi r squared, and since r is 1, the area is pi. So the area of the sector is theta divided by 2 pi times pi. And what's beautiful is those cancel. So I know this is going to sound weird, but the area of that sector is simply the angle divided by 2, as long as, and this is the kicker, the angle is in radians. Right? That's what forces us to go in radians, that and that. All right, so what do we now know? We now know that theta divided by 2 must be less than or equal to 1/2 tan theta and greater than or equal to 1/2 cosine theta sine theta. All right, fair enough. Remember, I'm trying to prove that sine theta divided by theta as theta goes to 0 is equal to 1. Well, one thing I'm going to do is I'm just going to multiply everything by 2. All right, that way I can get rid of the 1/2s. The other thing I might do is I might rewrite this as cosine theta divided by sine theta. Okay, well, I'm now going to pull something. I'm going to divide every one of these quantities by cosine theta. Now, generally speaking, you want to be a little bit wary in inequality work when you divide by a quantity, because if you divide by a negative, you have a problem. Right? Side note, oh, that was weird. We all know that's wrong. It's sine theta divided by cosine theta. Just strange. Mental hiccup. Anyway, by the way, here, instead of dividing tan theta by cosine theta, I decided to multiply tan theta by 1 over cosine theta. It'll just be easier to really think about, right? So I'm going to divide everything by cosine theta. No, I'm not. No, I'm not. I'm going to actually divide everything by sine theta. Boy, I tell you, the mistakes are just rolling. Hopefully my 4 honors students will forgive me. Anyway, still, the argument is the same. We have to be wary about dividing by a quantity. Is my face turning red? Multiple mistakes. We have to be wary about dividing by a variable quantity because it could go negative. That's why I'm going to orient us in the first quadrant. I don't have to worry about that. Sine's positive. All right? So after all is said and done, this is the inequality we're sitting at. Cosine theta is less than or equal to, right, theta divided by sine theta, which is less than or equal to 1 over cosine theta. Now, this is where the best named theorem in all of mathematics comes, right? What's known as the Squeeze Theorem or Sandwich Theorem. Either way, I'm gonna write it in red. I actually like squeeze. That's my favorite. The Squeeze Theorem. All right. And here's what the Squeeze Theorem says. It says, look, this quantity, which is what we're really concerned about. I know it's sine theta over theta here, and it's theta over sine theta here. But this quantity that I'm worried about is sandwiched or squeezed between these two. So I could ask myself, well, what is the limit of cosine theta as theta goes to 0? Well, what is the limit of cosine theta as theta goes to 0? Well, it's equal to 1. And I could ask, well, what is the limit as theta goes to 0 of 1 over cosine theta? Well, that's 1 divided by 1, so that's 1. So if the two things on either side of theta divided by sine theta both head to a limit of 1, then the thing that is squeezed in between them must also head to a limit of 1, right? And so since the limit of theta divided by sine theta, ooh, I am near the bottom of the sheet now. Since the limit of theta divided by sine theta is equal to 1, we can invert that and say that the limit of sine theta divided by theta as theta goes to 0 is also equal to 1. That is amazing, isn't it? And sorry about the mistakes and the messiness and the fact that it's all the way at the bottom of the sheet. It's still amazing. What's really kind of cool is that you really kind of have to look hard to see where the radian thing came in. It came in right here. Really, just at that point where we were setting up the area of the sector, right? And that led us to an area formula for the sector that was very, very simple. Theta divided by 2. All right, well, you can't go through calculus without seeing one of the most famous proofs of one of the most famous limits out there. So hopefully that helped a little bit. I'm going to clear out the text, so pause the video now if you want to think about any of that material or copy it down. All right. So that's it. That's all there is with really trig limits. Thank you for joining me. This has been Kirk Weiler for Arlington High School Math 4 Honors. As always, access that worksheet by clicking on the description underneath the video. And until next time, keep thinking and keep solving problems.